Welcome to Best Talks. This is where you faculty get to be the stars and kind of share your insights from the perspective of people trying to improve the building's workforce related to building operations and building technicians, right? We're all here because we know that buildings won't run well all by themselves. They just don't quite work that way. All right, so let's go ahead and get right into this. All right, I'm going to turn it over now to Bob Clark. Bob was one of the mentors. In fact, all of the presenters here were mentors during our BAS workshop. And just briefly, for those of you, of course, who were present, it was a hybrid format. We did all of our meetings and lectures online, but you were all back at your college labs working on your trainers. So, Bob, go ahead.
So good to see everybody in here. I kind of got to see some of the folks here. There might be a couple of new folks I haven't got to hang out with yet, but I always love these events. I like when we get together and start talking about how can we further this type of education across the entire country. And I think that's what BEST does well. I was going to discuss just a couple of the key points that, we had covered, I think, during that workshop. And that was one of the most important things is to establish a hands-on lab activity in an exclusively online environment. That's not very easy to do. And in today's world, that was actually pretty useful for a lot of folks, I think, across the country that could both work with students programming online and at one point, obviously, come into your lab and commission that particular program by what we actually went over, which was, the application of analog output controls and controlling PID loops, very important in building automation systems everywhere, and it's not understood enough. And examining the challenges of basically a complex control circuit or sequence. And this would happen to be in a VAV box that is in every single building in America for the most part, not every single, but pretty close. It's a pretty prominent piece of equipment. And understanding the basics of that variable air volume controller. Once you start to control it, you really start to understand it intimately and get what's actually happening inside of that VAV box so that you can take that, teaching perspective to a completely different level. And then demonstrating the ability, I thought, was one of the key outcomes of that whole workshop, the ability to teach or learn that complex sequencing circuit, which I think is great for everyone. And I love seeing the pictures of everybody's lab and the development of it. It was great. I kind of reviewed some of these PowerPoints before we'd even gotten into it. And it looks like everybody's doing a lot of work keeping stuff moving forward. Even though in this day and age, it seems like we're moving at the speed of molasses, I still think we're light years ahead from where a lot of programs were, back when I think of the beginning of BEST. So 2012, Larry? Was it 2012?
Yeah, we started fall of 2012.
Atlanta in 2012. So, it's great to see the impact across the country and different labs and the development of it. So I'm looking forward to hearing these presentations from the different schools that are opting to, show everybody what they're actually getting into. So,
well, let's go ahead and start with our friends at Sacramento City. That's Richard Gentry and Brad Prudhel. And I'm glad to advance the slides here.
Thank you.
Hold on a second.
Now, do we want to hold all questions to the end, Larry?
Yeah, let's see how it goes.
I'm open to questions at any point because I think we usually forget some of them. I'd just like to introduce myself. I'm Richard Gentry. I am one of the professors and the new department chair at Sacramento City College. And I'm here with my cohort, Brad Prudhel. And I'll actually let him lead it because he was actually the head on this project.
As Richard's mentioned, my name is Brad Prudhel, and I am a cohort of Richards at Sacramento City College. And when this seminar came out last year, I was actually really excited about it. When I decided to build this trainer, I wanted to try to mimic what we're in the process of building in our air balance lab. We put up a fan. We've got multiple VAV boxes. Some of them are cooling only without a reheat coil. Some actually have a reheat coil on them. And so I wanted to build a miniature lab of what we are actually putting up in the ceiling in our lab environment. So I picked up a variable speed fan, as you can see on the right-hand end of the trainer right there. And then I coupled it together with the reheat box. At the suggestion of Richard, we decided to create a 90-degree elbow so that we could kick the air straight up instead of out of it as in front of a student. Now, there is supposed to be an inspection door on the end of that elbow. And in a couple of slides, you'll actually see my drawings that I drew up for the fittings. The shop that fabbed that elbow up cut the inspection door on the bottom side of it. So there was no inspection. My intent was so that the students could actually look in and actually see the actual damper in motion. I need to modify that elbow there and cut a hole in it and put a piece of plexiglass over it. And that'll be done probably this summer sometime. Here's the parts list that I created when I ordered all of the parts for it. The very first item is the 6-inch VAV box. Then the 2-row hot water reheat coil. There's a Belimo 3-way ball valve and an actuator with a 2 to 10 control input signal. There's a Veris transformer. Then the Fantech 6-inch inline fan and a remote potentiometer. I've got my temperature sensor with the shunt zone sensor. Then I've got my duct probe for the discharge temperature sensor, and then the EasyIO VAV controller with the actuator, and then the elbow transition and the angles which were donated from a sheet metal shop that I work for. I work for Solace Enterprises, and I talked to the owner, and he donated the material for this project.
Yeah, Brad, if you had to approximate a cost on the donated sheet metal, would that be, say, an extra couple of $100?
Yeah, probably so.
Okay, all right. So we're probably looking at a total cost of around whatever, $1,200 to $1,300.
Yeah, I would say somewhere between $1,200 and $1,500 would be a good number. And here are my drawings that I drew up that I submitted to the fab shop. The top one is a side view of the elbow, and then the bottom or the center one is the end view of the elbow that I made up, showing the transition in place. And then this is just an end view of the reheat coil and the VAV box, so that they knew the dimensions to make the elbow and the transition. All right, we are here in progress. You can see that I mounted the on the left-hand side, working left to right, the fan, and I've got the potentiometer mounted on top, and then I've got the cabling in between where my power supply is coming in, sitting right on top of the VAV box. And I chose to use SO cord so that I could actually plug it into a 120 volt power supply. I wanted to make this thing portable. I've got my elbow up there. I've got my piping and my 3-way valve and actuator up on top. And what you cannot see is there is a hot water heater in our lab, probably about 15 feet away. We actually moved this table closer to the hot water heater, and we connected it to the hot water heater and had water flowing through the coil, and you could actually see the discharge temperature rise as the three-way valve was opening up and allowing flow through the coil instead of bypassing it.
Now, Brad, you all chose to add that Belimo valve with an actuator,
Yes.
right? Yeah.
Yes.
And
I wanted to make it realistic so that the students, when I actually do this, the students can actually see, physically see, instead of having to imagine. Because one of the hardest things for our students is they're so new, they've never seen anything like this. I can tell them what should happen, but when they can see it, it actually sets it in.
Yeah, I think what I'd like to stress on that is, right, too many times we see, right, a sensor mimicked with a potentiometer. And then I find that there's a disconnect in our students when they're setting that pot, but they don't really, they don't understand it's a real temperature. So Brad's pushed this lab so that we could actually, right, heat the air coming out of it and control it. And I think that is that next step that we need to bring some of our labs to, is that it's truly functional, so that we're not mimicking something where we find that disconnect. It's truly functional.
And I'll take this a step further. The VAV lab that we are building, like I said earlier, has a combination of cooling only VAV boxes and cooling with reheat coils in them. If you look at the far right of this image right here, you can see a VRF system that was installed, furnished and installed by Train. There is a heat exchanger that we can circulate water through and absorb the heat from the refrigerant that we are going to pipe out to the reheat coils out in the air balance room that we have, so that once again we have a realistic environment for our students. They will actually see the discharge temperature rise in the heating mode of the VAV box. And actually, we're going to take that a step further, because I think I'm going to tie it in. We have a hydronic hot water heating boiler out there, and I'm going to tie it also into the boiler system, so that when we're running the boiler system, we don't have to actually run the VRF refrigerant system. This is just a different view. It's an end view. You can actually see the three-way valve a little better, and it's piping into the reheat coil. I do have unions on the reheat coil so that I can, on both sides, so that I can disconnect that assembly, because it does stick out quite a ways. Makes storage a little bit easier. And it makes transportation a whole lot easier. I don't have to worry about knocking that off or bending the copper tubing on the coil, destroying it.
Part of Brad's vision that he's not offering up is that we can take this out, ideally once we're well set up to career fairs, things like that, and have it actually running in front of students. We might not be able to do the reheat, but it's designed such that we can get in and out of vehicles and show students what are going on.
You might also mention a little bit about the trailer that you use for outreach. I know we don't have a photo of it here, but we have seen it at previous workshops.
Brad, if you talk for a second on the trailer, I will grab a picture of that just for those who are new, because I know where I have one.
A few years back, we purchased a trailer to take out to our outreach, use for our outreach program. And inside that trailer, we have various refrigerant trainers. This new VAV trainer will go inside of it. We have a portable mini split system that we roll up in there. And it gives the prospective students an idea of what we actually do in our classroom and in our labs. I believe this is, where is this? This is not at.
This is the last career fair we set up for Bose last summer.
Okay, I wasn't there, so
Yeah,
I don't
you didn't go to that one, but it kind of gives a idea what we can do and what we can pack inside of that trailer for our events. The trailer's all set up, our tents are set up, our canopies are set up, and we even carry portable tables, so we can do a full event right from it, self-supported, with chairs and everything packed inside. We just bring out. We have our own power supply if need be. But inside of it, as Brad was saying, right, we have a refrigerant system with glass cutouts and things, so we can actually see the refrigerant flow for students. We have a TV and sound system inside, so we can do our presentations. But more importantly, we bring out these tables and chairs, and we carry different lab projects, for lack of a better term, with us. And one of the ones that seems to go over really well is we do a flaring lab, where we just have them cut and flare 1/4 inch and 3/8 copper tubing, so they can get their hands on things in the field. And from past events, they're rounding up the kids from our table to shove them on the bus because they want to finish their projects. So it's been a hit.
And then, can I ask a question here, guys?
Please.
I'd like to see, or know, how many hours do you have in this VAV development? I mean, when you look at start to finish, and that's procurement time. If you got an estimate, procurement time, dealing with, internal administration to get funding, that's an important number, for a lot of people to know if they're going to go down that road. How long is that going to take?
I'll go to the funding, only because I'm dealing with that right now. Right now, we're doing pretty good at our campus. We have funding, and we have backing. So for us, it was pretty easy as far as the funding stream goes. All we needed to do was identify our quotes, and it was signed off and supported through Dean and all the administration. So
yeah, and I wasn't necessarily talking about do you have the funds or not have the funds, but
just
what kind of time frame do you have on from the purchasing to the end build? How much time do you have wrapped up in, just say, one of them, so
Brad?
people have an estimate of what kind of time?
Oh God.
Now you see what I mean? There you go.
I would probably say that I have 80 to 120 hours in it.
Okay.
But that was the design.
That was first off envisioning what I wanted, then figuring out my design, and then my parts list. The hardest problem that I had was finding a vendor that I could purchase the EasyIO controller from. And I know it's a Johnson controller, and I originally went to RSD, which is a vendor that we use quite a bit, and it's also a controls vendor, RSD Total Controls. And they are a Johnson FX distributor, but they cannot sell the EasyIOs. Then I had to track down an EasyIO vendor, and that happened to be Control Co in our area. And once I located them, it wasn't hard dealing with them. So I would venture to say that I have between 80 and 120 hours vested in the inception to completion of this project.
How many hours do you think we had in actual build, though?
In build, probably I'd say 8 hours to build that. I think we did it in 2 days, and I know it wasn't 2 full days. So I'd say 8 to 12 hours.
Yeah, it didn't take us long to build it.
Yeah.
It took longer for him to design it, and we could knock these out now pretty quick.
And I'll take it a step further. DDC is the now and the future, but there's still a lot of VAV systems out there, and pneumatically. And what I see, because I'm still a service technician, I still work out in the field, not as much as I used to. I see a big disconnect and a misunderstanding of how to calibrate thermostats to a VAV controller. Everybody thinks you calibrate it to 9 PSI and you walk away, and that is so incorrect. It's not even funny. So I am developing and I'm building a carbon copy of this. Matter of fact, I just got all the parts. I need to draw up my drawing for the sheet metal because my VAV box is slightly different. So I need to draw up my drawings for my fittings and get those submitted, because I'd like to have this thing put together before mid-semester, spring semester, because I do pneumatics in my automated controls 1 class at the end of the semester. And I want to have, since I don't have my VAV trainers completed yet, I want to have my demo that I want to use in my classroom before I actually take the students out to the lab area. Because what I forgot to mention earlier on my VAV trainers is I had the VAV boxes custom built. They are dual shaft. I've got a shaft coming out of both sides of my VAV boxes in the trainer room. And I'm going to have pneumatics on one side and DDC on the other. And all I'll have to do is loosen the linkage on whichever control system that I'm not using. So I want a classroom demonstrator so that I can demonstrate what the purpose of the lab is to the students, and then have them go out into the lab area and actually perform the lab. So there's a huge misunderstanding of pneumatic VAV boxes, and I want to incorporate that in my control system. Even though it is old technology, there is still a ton of it out there. And the people that understand pneumatics, they're my age or older, and they've retired.
Brad, will you be using this lab installation in the lab?
No, this is actually going to be a demonstrator for my classroom. When I bring out the VAV lab, I am going to be having this demonstrator, this trainer in my classroom, and I will demonstrate to the students what a functional VAV trainer is, or a VAV is. And then we will go into programming and commissioning, and they will go out into the lab areas to actually commission it.
Is that an expected result or unexpected when you started the project? Did you think you'd be able to?
It was expected. When I at the inception, as soon as I seen the email about what our topic was for the seminar, I started thinking, because I knew we were going to have to build a trainer. I wanted to build a trainer that I could utilize in my classroom environment as a demonstrator, because I like to walk through the lab, especially a complicated lab, with my students first, and then allow them to go out and actually perform the lab. That way I'm not hands-on with their lab. I'll be there as a guide and not doing the actual work. I want my students to do the work. Everything from creating a wiring diagram to creating a sequence of operation to programming, downloading to the connecting and downloading to the controller, and commissioning it.
So you guys, that's an absolute great job over there. We've been to your campus too. A few of us actually probably in this room still, but yeah, nice work, and keep it going. Look forward to the developments. And I think we're turning this over next to Wake. We're going to be moving over. But yeah, if anybody has any questions, I think we can just, if you guys don't mind, we can send emails out, and
Please.
hopefully, yeah, that sounds good.
Hello.
All right.
Whoa,
Next up,
the voice of
All right, how about
God.
this time?
the Steam Master.
Hello, everybody. Yes, I got the steamboat back on the water. It was down all summer with a broken crankshaft. I'll send you side pictures. Andy Smart here. We've got Connie next to me. I don't know if my screen sharing is still on or not. Yeah, there it is. So we got Connie, and I also have another colleague of ours that's joining our little team here, Zachary Taylor. He's not on the slides, but we're excited to show what we've done here at Wake Tech to build our not quite so portable VAV system. So let's see what we've got going on here. Here's our mess that we've started with about 1.5 years ago. And so we've got 2 air handlers in place now. Ultimately, the purpose was 1 air handler is going to be tied to the 16 VAV boxes that you can see spewing throughout the room. And then there's a second air handler to the left here that's going to be tied to other VAV boxes. So the 16 Manila VAV boxes are all cooling with hydronic reheat. So they're exactly the same size throughout. So we can have 16 students individually doing, everybody gets a pair of controllers, everybody gets a VAV box, and share the love. So the second system is going to be right here. We've got enclosures around the room and 2 students per enclosure, but so we'll have a controller and accessories on the left and a controller on the right for each individual student, and they'll be able to climb an 8-foot ladder, and it just fits underneath the box, so they can get access to the box and see everything. So when I was designing this, I put in, had the local duct shop make some nice spiral duct for us to make it look really pretty. And they put in these saddle taps, and then we put in some single wall duct to feed the VAV boxes. I had a struggle to align all the boxes. I was going to just put elbows at the bottom of the drops and drop them right in and have them all in line. And then our engineers stated, well, you've got to have a little bit of laminar flow before the VAV box to have so the air sensors work properly. So they went a little overkill, but cantered every one of them at about 30 degrees so that we have good access to the enclosure or to the VAV box for the students to get in there to the components and also the airflow component. I also played with putting everything in and not messing up the lights that were in the room. So trying to keep everything functional throughout the lab. So everything is in the background, and in the foreground where we are sitting right now, we do have the ability to have lecture. And you can hear the folks next door. So there is a wall that's not complete. They didn't finish the wall over there on the right-hand side. It needs a few more bricks. Anyway, that's for this slide. Oh, here we've got, I also put in a cable tray to go side to side throughout the room and then forward and aft. And we're able to run network cables and the control cables from enclosures up to the VAV box. Got 2 enclosures over here, 1 for each air handler. The air handler on the right is going to be primarily for the students to do everything from install the sensors, run the wires every semester or set of semesters for our students, program everything about it and get it to work. Outdoors, we have 2 chillers, 1 dedicated for this air handler and 1 dedicated for this air handler. We are procuring a boiler for both. So it'll be a single boiler and we'll be able to, we've got preheat, reheat on the 1 air handler. We have electric preheat and hydronic reheat on the 2nd air handler. And then we have hydronic reheat on all the VAV boxes. So we're going to have a lot of demand for our water, and we're working pretty hard designing that. Maybe Bob can come down here and spend a couple of days and go out on the boat, and we can finish designing this hydronic system.
I'm in.
All right, let's go. So we also, our IT folks donated a couple of used switches, and they gave us an enclosure, and it's actually sitting behind all this screenshot here. And we've abandoned that, and we put the switches up here on this tray, made a little shelf for it, and it's working out really nicely. So we're trying to, and one of the things when we try to lay this thing out, ergonomics has been kind of the big thing for us in this. Every time we've gone or I've taken classes, getting the instructor to come around to look at the students, what's going on. You're always fighting with tables and wires and computers and now power cords. And we're really trying to alleviate that so that we can really focus. Because this semester I've got classes with 16 students, and some of them are just myself at times. And you all know that's not easy. And then trying to keep them from blowing stuff up is another challenge. So we're finding a ways around this. We've learned how to connect to the controllers through some of the best activities as far as a peer-to-peer, put a computer directly to the controller. The class that we taught this summer or this fall has been a networking class, and then we have a programming class. In the networking class, we've got switches that we've kind of incorporated. And then we've downloaded some free automatic DHCP server software to be able to dole out the IP addresses. So we're learning that's kind of got to be kind of early on in our program. And the other thing we have in here, we've got a wireless point, so the students can come in and connect to our local area network that's completely independent of the school. So we're able to have the student away from the controller so that they can be over there on a desk, and then you can walk up to the wiring and be able to get around easy. And that's really been a very clear focus every time we try to put something together here is keeping the ergonomics. So let's see what else we got. Here's a close-up of the VAV box. Again, the straight sections. At some point, we'll get some students to finish the single wall here, maybe mastic it, maybe put some, wrap it with insulation. Once we actually start pushing some cold air through there, I'm sure it'll start sweating. We are behind on hooking up the hydronics for the reheat. We've got, in the enclosure, you can see here, I've got these electrical connections. And so the students have run wires to the enclosures, and I have the electrical connections color coded between here and down below. So it allows us to check the students' work a lot easier. What we're going to do now, as soon as the budget opens up in January, we're going to order some mailbox lettering so that everything's lettered A, B, C, corresponding, because students are trying to control the wrong box. Yeah, it happens all the time. So here's another shot here. We've got the actuator, JCI, I think it's Granger Special, probably in the $100 range. I think these are Dwyer differential pressure sensors, and a transformer for future, if we want to pull this out and put a standalone controller in there that needs its own power supply. During the summer exercise, we needed to get things up and running, so I just found a set of heat strips off an old system and took them half apart and wired it ad hoc. And I was kind of concerned that it was going to be toggling on and off too fast, but in reality, it took a while to heat up and cool down, and it actually worked out really nice. One of the items that was suggested during the summer was that variable, the relay that's a variable relay, and that was new to us, and we didn't get that in time, but this worked out just fine, being just a single stage on or off. If I had to do it again, I probably would have gone with the electric reheat and forego the hydronics for each one, but we wanted analog outputs. So Connie's comes from a programming background. I come from an HVAC background, so this all made sense to me. And I think Robin had the same issue. Is it wasn't sequential, and we've learned that in some of our programming classes. that there's issues, but we're starting to see the benefits of this type of programming versus sequential. One of the things that, trying to make these slides for this little presentation is like, okay, what did we do? And as we've all learned that there's a place for comments, but that comment is one comment slot for the entire page versus each object having a comment like you could in some other line code item. So, it's too bad we can't, maybe Robert can go and talk to the JCI and see if they can't make an improvement on that Sedona for us. So in this fall, we've kind of implemented using the contemporary controls. So we're using both contemporary controls and EasyIO in the class for various reasons. But right now we are running the sequence where the students are driving an input with the differential pressure sensor, doing a literization, giving an airflow, and then able to play with the PID, or at least the PI portions, and see real time. We've got the air handler up and running, so we fire that up, and actually that's on a PID, so we can hear that ramping up and down and oscillating, and they can adjust that, or we adjust that, and they go to each box and they can adjust their PID, and we can watch it go up and down. And it's kind of exciting to see that, okay, we actually can start teaching PID and with something with real feedback. And I think somebody mentioned that before. It was it's kind of hard to really sense the rheostat you're tuning to see its actual temperature, but to see your actuator and see the value of the airflow is really the students that are embracing this is really a great thing. Yes, again, we're making our wiring easier. Waiting on those little plastic trays with the little holes to make everything nice there. I think I've mentioned this already, but there's recent carnage from, it's just so easy for the students to hook up their analog output to something that's got a little bit of power, and next thing you know, it's a problem. So we are choosing the EasyIO and the the BAS 22 with contemporary controls and the Raspberry Pi. We're doing a little bit of everything. We've introduced in the networking class some MSTP, and then we've found that the EasyIO is a nice way to convert that over. And so it's definitely not a portable project. It's talking 10 to 15,000 for the air handler, depending upon. I think the second one was a lot more, plus the duct work. We've actually got it ducted to the out of doors. We really didn't intend it to be portable. So here's a couple of the items that we've had. We've got Tuttle and Belly, the JCI actuators, Ashcroft. One of the items, when you do get your differential pressure, take a look at your VAV box first to see the limits of the airflow. The limit of the airflow is probably 300 CFM, and that doesn't quite make it to 1 inch of static. And it would have been nicer to have a 0 to 1 instead of a 0 to 2, because that would have just given more range of the 4 to 20 milliamps. And that's our lab in a nutshell.
Man, Andy, it looks like you guys are coming along really well.
Thank you, Bob.
And Andy, you fully intended to use this in your instruction, it looks like. Yes?
Yes. Yeah, we're implementing it right now as we're speaking. And then we're seeing things that are working and things that aren't working. So.
Anything unexpected in this project that you weren't
so just the layout of things. I guess it's we as instructors, we go out to these best workshops and we can implement some of these scenarios rather quickly, and to be able to slow down quite a bit for the students that don't have the backgrounds that we all have is paramount. But yeah, we're I'm not too much unexpected. It's just trying to fit everything in here and make it a realistic mechanical system. and then roll from there. That's what our biggest goal is, man. We got the NSF grant, and we're spending it as much as we can.
And your outdoor air, Andy, if you don't mind me asking about that, I think that's just a great way to bring that mix in.
So yeah, we've actually run that scenario where, hey, you know, if you know we dictate the amount of outdoor air CFM per activity per person. So we bring that in, and we can do the delta T, or excuse me, we can do the OAT, the return air temperature and the mixed air temperature, and we can run that real time and actually drive the mixing box. And you know, I could sit here and talk about it all day long, and it kind of doesn't really sink in, but until they do it. And we have had some cooler days where we've done that, and this is, for me, it's been super exciting to have it real activities on a real machine, that we're not breaking somebody else's, you know, a machine that's actually being used for offices.
Well, if I can leave you with one last thing after that great presentation, Andy, it would be one of the Bob proverbs, that is, there is no such thing as student proof. There's only student resistant.
We're doing what we can. Thanks, Bob.
Great. No, great presentation. Great to see the developments in your lab.
Thanks.
Cool. We'll get Larry to get us moving forth here and share the other presentation.
And now let's move on to our friend in Louisiana, Robert McNabb at Northshore Technical Community College.
Mr. McNabb.
So can everybody see that?
Yes, we can.
Outstanding. Okay, so hello. I'm Rob McNabb, and I teach at Northshore Technical Community College in Louisiana. We're located in Hammond. And this is our kind of trials and tribulations of trying to develop some kind of trainer lab here. And it started early on, a couple of years ago. But when I initially came down here, we had the initial donations from Contemporary Controls, the BAS 22 controller. And building from that, when we were going through our controls, we always started at basic electricity and moved into controls. And we liked the idea of having students move from one to the next. And some early versions of these trainers that we had is we just took blocks of wood and applied various materials to it. And we started from just hooking resistors up to batteries, and then we moved up to electrical and residential units, and then commercial type of control sequences. In the picture on the left, you can see that there's a 3 light bulbs there and just relays, and what that is simulating a wide delta compressor starting type of switch gear. And then in the picture on the right, there's where it is again portable on a block of wood. It was the contemporary controller, and it has Bob's original configuration for a thermostat there, and the students would use a laptop to go through the software. And this lasted pretty good. Emphasis was on operational theory and not the end product. And even though it got the job done, it became clear to us as we advanced through the curriculum that it wasn't a very realistic application. And the biggest issue we had was just consistently sloppy wiring from our students. The good side of it is students got introduction to programming and relay logic very soon after they were doing basic electronics, and it would stick in. Wanting to improve on this, because my lab was looking like somebody's garage, I decided to see if I could get a Perkins funded grant to get some panels put into the lab. And the result of that was version of trainer, which did what we did on the blocks of wood, but it was much more realistic as far as commercial application. The good side about this trainer is that this is not just a BAS trainer. It evolves into a BAS trainer through the curriculum. So a student can wire up basic circuits with a DC power supply, 12-volt DC, and then basic just resistors in series, resistors in parallel, and then wiring it up so they could check the voltage drop across each resistor, and then advance into, okay, running lights off of it, and then start doing sequences of operation. They're able to mount more and more advanced equipment into the panel. At the bottom here, there's three little relays there. Each relay has a different voltage. There's a 120-volt coil, and then there's a 24-volt AC coil, and then a 24-volt DC coil. And so they're using different voltage power supplies and running lamps. And these lamps have different voltages. On the top, they're 110 volt, and on the bottom, they're 24 volt. And we have these momentary switches on the top here, and then they had a covered single pulse, single throw switch that would lock in position. And these were single pole double throw switches that would return to their open position for momentary, like a push button. And we were able to get more and more advanced relay logic as they progressed. And then towards the end, then a contemporary control would be mounted in the board, or mounted in it, or on a panel next to it and wired in. And then they would be running lamps off of different algorithms on the controls. That worked out really, really good until one student put a wire in the wrong place and blew up our controller. But it was a good dry run as far as this can actually work for the whole program, from basic electrical all the way up through advanced controls. So unexpectedly, we got a donation from CompuTrolls for all 6 of these units. I had students build 6 of these boxes, and they had a pretty basic layout. They have indicator lights, they have DC and AC ammeters and AC and DC voltmeters that can be wired into the circuit for safe reading when they turn the system on. And it has test points on the front that are numbered and correspond to a terminal plate inside that allows students to take safe readings of voltage with the panel closed and the power on. In the more advanced classes, the single pole, single throw switch is replaced with a room sensor. And that room sensor, when they install it, it has nothing on it. And then they're required to set up the program for that room sensor for that particular zone and the particulars they're given. And then they move from that to input and output analysis. If I have this input in, I should have this output out, and they could use it to actuate a light and get basic functioning going. So this once I got all the stuff set up from CompuTrolls, we had one of these panels. There's 6 of them in the lab. One of these panels on the end has the master controller on it, while the others just simply have the terminal boards and power supplies. But they also donated 6 VAV controls, and those all communicate to the master control. And so you can run all of the labs off of that one master control, and then that's where their interface is. So they start with a blank canvas, and then it kind of grows into a more and more sophisticated wiring, where they have to also manage the wiring in the panel. And this was our first use of it, when we actually, first time we actually used it in a training program, and they actually ran it. And so you can see right there on the most complex panel we have, there's the outdoor air sensor, 10 kilo ohm, laying on top of the cabinet. And that's interfaced with the 8LX controller from Computrols. And then they have 6 VAVs, one at each station, and a sensor that's communicating with this controller. We were able to get one VAV box donated from one of our local companies. On the first iteration of this, we had one hooked up to a VAV box, but the other controllers were on a table near the panel so that they could see the actuators just move. But they were able to see the first one actually move a damper on the VAV. When we get the funds, we're going to have 6 VAVs. They're going to be mounted on the ceiling in a mock drop ceiling, and we're going to duct it into one of the donated units from Rheem as the air handler, and they'll have 6 zones that'll operate 6 separate VAVs for actual airflow applications. This one was just, since it was the first time running it, we used lights to simulate activation of the 480 volt electric reheat coil on it. And what we did is we operated the switch gear, but the contacts on the switch weren't connected to any 460 power. They just activated the light to say that the heat was on. But we're wanting to use also hot water reheat on some of the zones. What we have found is that this is excellent. When the students are working with these panels, they start with the panels pretty much empty, and then they do their basic circuits. And then as they advance into the commercial controls courses, we have 2 commercial control courses. We have a commercial AC controls course and a commercial refrigeration controls course. And even though they have different applications, it gets them into watching these evolve into a more and more sophisticated circuit. So it's almost a cradle to grave type of scenario. And then when they're at the end of their final course, they dismantle everything. And here's another view of our first operational configuration. Now, to get the airflow for it, all we did is we took out a residential fan and set it on the table, wired it up, and have it blow right into it just to see if we could get the sensor to work. And we were able to get it to have the sensor work. And we're going to have a more sophisticated. So I don't have prices for this, but I'll make prices available through a PDF for the actual electrical boxes. The controls, all the controls were donated, so I don't have a price for those. But I do have an invoice for all of the cabinets and all of the lights and all of the meters and power supplies and components.
Robert, you mind if I ask, do you punch all those holes yourself in there?
I had the students do it. What I did is I had the students mark them.
They do them manually, or did you guys have a knockout tool?
Here's what's really cool about that. So you see the conduit?
Yep.
The electrical students put that conduit in we have multiple programs here. So the electrical students conduited in. The HVAC students marked the panel fronts for the small holes, and those went over to our machine tools technology students. The machine tools technology students bored the small holes, and then the large holes, the HVAC students, the large holes for the meters, the HVAC students used knockout kits to do those.
Nice. Yeah, it looks like it's coming along great, man. It's one step at a time. And the tables versus where those controllers or the boxes are sitting, yeah, it seems like it's manageable and people can get around them.
Yes, and we're trying to rearrange your lab a little bit better, but right now, since that picture was taken, we had a different semester clutter everything up, so we're going to have to clean everything up again. So we kind of have to do a lot of reconfiguring in the lab, but we still have a lot of room to work with. And there is a table between each of those panels. So
now, Yeah, it seems like you got great workspace. What do you think you have as far as time invested in this? And I'd ask that same question to Andy as well. If you guys could both chime in, because that was an important detail. I think anybody that's interested in going down this road needs to understand of what it takes in regards to time to put that together. And I meant to ask Andy that too. We're getting moving.
I didn't want to build anything, so I made the students do it. But the cabinets and the smaller components all arrived right before the COVID shutdown. I built a prototype while I was isolated in my house and brought it back when they started letting us have students come in at a limited capacity. And then limited capacity students spent the summer semester and fall semester building those cabinets. And then the following summer, after COVID, was when we got the CompuTrolls gear, and then that setup was made during the was designed during our summer workshop. It was designed and basically put together, but it was made operational and programmed by students, and that was 6 zones, all programmed and functioning for the following spring semester.
Good. So it sounds like you just acquired the materials and you put the majority of the build on the students, which is a great idea.
Yeah, I'm impressed that you were able to coordinate between different programs to get this done. There could have been a number of snafus along the way. So
Well, I got to knock on wood, but
right.
Everyone seems very willing to work together. They're a pretty close knit group here.
Southern hospitality.
There you go.
It's the catfish. So Rob, you mentioned that the students, start off with the basics on these panels, cabinets, right? And then they build towards increasing complexity. So, does a student or whatever, a small group of students, they stay with that one panel throughout a series of courses? How does that work at in your program?
Larry, I'm very sorry. I had a technical glitch, and I lost some of your audio while you were asking your question. You don't mind repeating that, do you?
Oh, sure. No worries. Right. You mentioned earlier that the cabinets are used by students first doing more basic sorts of tasks and then growing in complexity, right? So in your course sequence, do the students, they basically, right, they are assigned a cabinet or panel, right? And as they go from course to course, they continue to, build on their own work.
That's correct.
Okay.
On my large classes, I've been able to have 2 per panel. And how it works, they're doing a series circuit. So they wire in a series circuit and then they dismantle it once it's been tested. Then they do a parallel circuit, then they dismantle it when it's been tested. And then by the end of that semester, I'm saying, okay, I want to be able to turn the power on the box and hit this button down. And I want this light, and you label this light compressor start, and then you'll label this light airflow. And you start working them through a sequence of operation. And so by the end, you're giving the students a sequence of operation, and then you're giving them a schematic and a wiring diagram. And they have to wire it all up, and then it has to meet the sequence of operation.
Mm-hmm.
I have a question for Robert Nirenberg, if he's in the room here. Robert, did these lab installations go the way you expected them to go? Are you surprised at the different ways people approach the problem, or?
So that's a great question, Peter. When we first started out this online workshop, I really wasn't sure what we were going to get. I knew we have a huge variety of creative people here within the BEST Center, so I knew we were going to get a good variety of systems. I knew some colleges already had a lab setup of some sort that would lend itself well to this sort of setup. Something more like Laney has or GPTC, where they already have VAV box setups. I knew Andy was building his lab out in the process. So the big question was going to be where we came out with the variety of portable trainers and their level of functionality. And the whole BEST Center teams did not disappoint me with the variety and the functionality that we ended up with. There were definitely some challenges towards product procurement right at that time period. So that was definitely one of the challenges that I know a lot of our folks faced. So, but they pushed through it, and you know, we got some really great results, I think.
All right, do we have any other questions? I know that a number of you attended the workshop. You know, at a later point, if any of you are perhaps interested in sharing your trainers, maybe to get feedback from, you know, these presenters or other instructors, you know, please let us know.
Yeah, I think this exercise was what we would call, or what the literature calls, adaptive expertise. People took the problem and solved it in ways that made sense on site for them. I think probably around the room, everybody approached it a little bit differently. But there's so much expertise that the BEST network has. It's amazing.
So, and if I could add one more thing, I think it shouldn't just be limited to this one training application, but what developments have been happening. I know Jenny Brinker's working on a VAV thing that's portable with television and relating it to a lot of other things and showing the graphics and the interfaces and what they could get into for outreach. So there's a lot of outreach opportunities too that I think a lot of people could benefit from hearing how different folks are working with them. I know Chris Miller is in the middle of his sustainability battery grant, but he's been working a lot on his HVAC lab, and there's new developments coming from him as well. So I think anything that even relates mildly to high performance building education, outreach, and building automation education, it'd be a relevant topic, or just mix it up.
Mm-hmm.
And for Richard and Brad, yeah, we look forward to seeing the next iteration, and hopefully this time the viewing window, or some people call it the truth window, will be cut on the right side of the ductwork. So
I want to see a steam coil on there too.
Kids don't have to lie down on the floor and look up.
Yeah. Well, right. That window was again, it's that we as technicians have long ago figured out where that damper is, but it was trying to give the student that definitive view of what's actually happening inside. So that idea of being able to see it. Right. He's working on the pneumatics. He's back now.
I've been back.
Well, you were off. I wasn't sure.
I forgot I had my video off.
But right, we're looking at how we can use this. I'm already reinvigorated and remembering that it's there, because I'm going to start doing outreach in January. We're allowing us to get off campus, and I'm going to see a local high school that potentially 30 to 40 students who might be interested in this program. So yes, that piece about how we can use it for outreach and how we can introduce this is something I'm even very interested in, because I'm an old white guy, and I know that how I got interested is not necessarily how everybody else did. So any feedback on outreach is great for me. What I'm working on actively right now is internships. I'm working with employers to actually open their doors to high school students for internships, as opposed to just college students, trying to get them into the industry and seeing what's available early.
Keep us posted on those outreach efforts. We could certainly do future best talks on that as well.
Richard, one suggestion that I have, you could also do job shadowing with high school students. So it's less committing than an internship, but you can learn so much just, observing somebody in their workday and seeing what they're doing, and it's really a great experience, and it's very compact, and but it takes a lot of coordination, of course.
Yeah, and thank you for bringing it up, because I'm only working within the constraints of what I know about my college. But with that, I'm interested in anything and everything we can do that starts making that connection early. And if it's something as simple as a job shadow, I just have to figure out who and where in my locality is going to make sure that it's all covered. Because that's the one thing I know I can do with the internships. There's already internship programs within the campus. So just trying not to reinvent the wheel. But if I can find somebody who's doing job shadows and can cover the paperwork and costs of insurance, I'd go that route.
Yeah, they're probably, well, hopefully you wouldn't get into
I want to be an IT pro.
a lot of that.
Yeah, no, it's just the one thing I know, that the internships, my college will cover lots of the costs for the employers. So there's not a huge impact on the employer side of it as far as costs. There's time commitment, obviously, right? That portion of it, but there's already a mechanism in place to help the employer. So I'm interested in, right, this idea of job shadows. I've got enough connections that I can start pestering people to tell me how to do this. But I think that's a great idea.
Well, thank you again, everyone. Thank you to our presenters / mentors. You know where to find us if you have any questions.
Appreciate it.
Thanks, everyone.
Bye, everybody.
Thank you.